Welcome to part 4 of the underwater world chase tutorial by PeerPlay. In the previous part we've recalculated the normals of the ground mesh. In this part we will start working on a post-processing image effect shader using Directional Simplex Noise. Here you can see one of the possible results we can get using this image effect. I am quite proud of this image effect I created. I think it looks very cool. Before we start working on the image effect, let's add support for a normal map on a noise ground. We can then apply some more detail so we can see the image effect applied more clearly. So let's open up the shader. In the properties underneath the main texture we're going to add a normal map. And this normal map we'll call the normal map, which is going to be a 2D image. And by default it's going to be a bump. Now let's scroll down to the subshader and add the sampler to the main text. We're also going to add the normal map. Now let's scroll down to the void surface, and underneath the smoothness we're going to say that o.normal is going to be unpack normal, which is going to be a texture 2D, and a texture 2D holds the normal map with the in.uv of the main text. Now that's all to make this support a normal map, so let's save this shader and go back to Unity. Now we see a new slot here and we need to have a texture and a normal map. A couple of years ago I bought this asset Yu-Gi-Oh's Underwater Plants, which contains some sea ground textures, so I will use one of the textures from this package. You can obviously find any texture and normal map on the internet or create one yourself. So I'm gonna drag and drop this one on the albedo and this one's gonna be on the normal. So I've just quickly set up the scene so we can work with our post-processing image effect. So we've got the camera a little bit behind of the ground, and the ground has some nice colors and the normal and texture map applied. So we can see some depth in our camera and we can see some nice hills. So let's start by creating our post-processing image effect. To create this we need two different things. A CSharp script to apply to the camera, in which we'll blit the camera image, and a shader to apply to the camera output. So let's create a new folder, and we're going to call this folder scripts. And in here we're going to create a new CSharp script, and we're going to call this the underwater effect. Now let's apply the underwater effect to the camera. Now let's go to the folder shaders, and here we're going to add a new shader, image effect shader. And we're going to call this the underwater image effect. Now let's go to the camera and we're going to open up the underwater effect. Now as we're going to create our image effect, we want to see the changes directly into the editor. So above the public class we're going to say that we're going to execute this in edit mode. And we also want the image effect to be applied to the scene view so we can directly see the changes, so we can add another parameter which will be called image effect allowed in scene view. Now the next thing we need is to make a reference to the material that uses the shader of the image effect. So we're going to say public material and we'll call this mat. Now all that's left is we're going to add a void on render image. So let's say void on render image. Now as you can see, it automatically set up the render texture source and render texture destination, because that is how the unrender image void works. Now all we have to do here is do a graphics.blit, and we're going to blit from the source to the destination with some kind of a material, and here we'll use the material. And that's all for our script for now. So let's save this script and go back to Unity, and this will now throw out an error because this material is still empty and it's trying to find the material and apply it to the camera. So the camera turned black, so we first have to create the material. Go to the underwater image effect and let's create a material based on this. Let's actually create a new folder for the materials. So folder, we'll call this materials. Let's drag and drop this material into materials. And we need to apply this material to the main camera, so let's drag and drop this material into the matte slot. And now you'll notice that the colors are inverted, and that has to do with the shader. So let me first rename the shader to noise post-processing. And let's open up the post-processing shader. Now the reason that the colors were inverted is because it says here that we're doing 1 minus the color.rgb, so it's inverting them. So if we remove this 1 minus, then we save it and we should see the colors back to normal. So we can see that everything we change here has a direct effect on the entire camera. So what exactly are we going to make? Based on Simplex Noise, we will do something similar to the image effect as we did with the ground. Imagine that each line in this grid is a pixel on the camera. The noise function outputs a single value between -1 and 1 that we will convert to a value between 0 and 1. We will convert this float value into a direction vector for each pixel on the camera. We will then shift the position of the current pixel into the noise direction. So I created this grid of gizmos to show you the directions. Also the colors of the lines change based on the direction, as a color and a direction are both a vector. So let's open up the shader and start writing out our image effect. We see that the shader is called hidden underwater image effect, and a image effect is often a hidden shader. But for the purpose of this tutorial, I am going to change this to pair play, so it's not hidden anymore. Now, just as we did with the noise ground shader, we're going to implement the noise simplex into this. So we're going to include this as well. So let's write include, and we're going to include the noise simplex.zg include. Now, just as we did with the noise in the noise ground shader, we're also going to apply a noise scale and a noise frequency, and we'll also add a noise speed. So let's go to properties, and we're going to add some variables here. And the first thing we'll add is the noise scale. So let's open that. We'll call this noise scale, which is going to be a float, and by default it's going to be 1. Now let's copy paste this, because we also need a frequency and a speed. So we'll change this to frequency, this to frequency as well, and we need a noise speed. There you go. Now, as you probably know by now, is that this is just the shader lab, and we have to include these properties in the subshader as well. So let's go underneath the include, and we're going to write a uniform float. And the first one we'll add is the noise frequency, the noise scale, and the noise speed. Now the next thing we need is to get the screen position. So let's go to the struct v2f, which means vertex to fragment, because this is a fragment shader. And let's add a new line, and we're going to add a float for, and we'll call this screen pos. And this will take into the text coord, but we can't use text coord 0, so we'll take text coord 1. Now in the v2f vert, we're going to calculate the screen pos. So we can write out dot screen pos that we just created is going to be, and we can use here the function compute screen pos. So let's write out compute screen pos, which is a function in the shader, and we'll take the o.vertex, and now we get the screen position that we can use in our fragment shader. Now onto the fragment shader. I apparently already changed this to color. This used to say SV target, but we are going to change this to color. Now let's remove these 3 lines, so we don't need them. Now to create the noise effect, we're going to use a 3-dimensional noise in which we'll offset the z-axis, and in the x and y axis we're going to input the screen position. So let's write out a new float 3 and we'll call this screen pos spos, which is going to be a float 3. And for the input we're going to use I dot screen pos that we declared in the v2f, and we'll get its x component. For the y position we're going to get the I dot screen pos dot y, and for its z position we will set this to 0, and we'll offset the 0 by a certain speed. Now, just as we did in the noise ground shader, we're going to multiply this by the noise frequency. Now, to get an animated effect of the noise, we can offset the spos.z by the internal clock of the shader. So we're going to say spos.z plus this a underscore time dot x multiplied by the noise speed. Now let's do the noise calculation, and that outputs a float value, so we're going to say a float and we'll call this noise, and that is going to be just as we did in the ground shader again. We'll get the noise scale and we'll multiply this by the snoise function, and in the snoise function we'll input the spos, which is the vector 3 or the float 3. Now, as the noise returns a value between -1 and 1, we're going to convert this to 0 to 1. So we're going to do +1 between parentheses and another parentheses to divide that result by 2. I don't know why, but for some reason I deleted this color, so let's write that again there. Now let's stop for a moment, because we need to convert this noise into a directional noise, but let's first see what this noise really looks like. So I'm just gonna return this noise into the camera so we don't see the rest of the camera anymore. So I'm going to say a fixed for is going to be called color, and that is going to be a fixed for of noise 1. So that should give us grayscales of the noise values. Now let's save this shader and go back to Unity, and now you can see all these gray values of the noise. Now when we play it, we can change the noise values in the shader. So if we increase the speed, you can see it changing more quickly, and we can change the frequency. So here we've got our noise. These are all values between 0 and 1, so they go from white to black, or from black to white. So now what we need to do is we need to convert our noise value into a direction, and I'm going to use good old MS Paint for this to show you. So let's create a circle, and to do this we're going to use a cosinus for the x. Well, I'm really terrible at writing with my mouse, so the cosinus is for the x, and for the y is going to be a sinus. And for this we need the pi, which is 3.14. So the pi will say that when we start here and do the cosinus, we'll go around, and when we are halfway around we have 1 pi, and when we go another time around we'll have 2 pi. And this will result in giving us an angle that we can normalize, and then we know in which direction we want to push our pixels. So the first thing we need to do in our shader is to define pi, because pi is not defined in the shader. So let's scroll a little bit to the top, and underneath the include we're going to define the pi. So let's write define, and we'll call this m underscore pi, and that is going to be 3.1419265359793238462643383279.5. That should be specific enough. So now let's scroll down, and we can use that in the fragment. So let's create a new line underneath the noise, and we're going to declare a float 4, and we'll call this noise to direction, and that is going to be a float 4. So for the x position, we're going to say cosinus of the noise multiplied by m pi multiplied by 2, because we're going all around the circle. And for the y-axis, we're going to not use the cosinus but the sinus, and we'll say again noise multiplied by m underscore pi multiplied by 2. And for the z and w value, we'll say 0, 0, because we don't need to use them. Now we're going to shift every pixel of the camera into a certain direction. So let's remove this of the color, and we're going to change this to text to the projection. And we're going to get the main text, which is the camera output, and we'll set its positions to i.screenPos plus the noise to direction, and we need to normalize this so it becomes between 0 and 1 again. So we'll say normalize the noise to direction, and we'll close this one off, and there we go. Now let's save this shader and go back to Unity. Now we can see some really weird stuff happening in the camera. Let's turn on maximize on play and see what is happening when we play it. This looks really cool, but it isn't exactly what we are going for. But this is what makes writing shaders so awesome. You sometimes get unexpected results, but that can bring you some new ideas you haven't thought about. So what is going wrong? The pixels are offsetted by the noise in a direction, but at this point it is moving them way too far. So we need another parameter to control the amount of the offset. So let's do that. Let's scroll to the top, and we're going to add another property, and I'll call this pixel offset. And we're going to call that pixel offset, which is going to be a float, and it will have a starting value of 0.005. Now let's add that to the subshader as well. So we'll write pixel offset. Now let's scroll down, and we're going to use that pixel offset in this equation. So let's multiply the noise to direction by the pixel offset. So with that in place, let's save this shader again, and let's go back to Unity. Now back in Unity, we can see our plane again. That's great. Now we can turn on this icon, and then we can see directly the results of what we will do with our shader here. So let me increase the speed a little bit to 20. I can already see it moving around. And we can also add some more frequency. I'll set that at 8. And let's set the noise scale to 2. So now we see some really nice results in the shader and in the scene view. So this comes to the end of this tutorial part. In the next part, we will create sliders on the CSharp script to control the noise, and we will take the camera depth buffer into account so that the noise will be stronger or weaker depending on how far an object is from the camera. This tutorial series is made possible by the amazing patrons at my Patreon. If you would like to support me creating free Unity tutorials about audio visuals, algorithms and shaders, you can become a patron as well. You will then get access to all exclusive source file content of the tutorials. Go to patreon.com/peerplay for more information. Special thanks to Devin the Dude and Fegter. If you like this tutorial, don't forget to hit the thumbs up. If you would like to stay updated to new release tutorials, subscribe to the channel and turn the notifications on. Hope to see you again in the next part. Happy coding!